So there is this kind of evolution where we go from geometry and to kind of naive geometric ideas to very technical aspects. So, of course, you have been through all this, but as far as I can see, you have always kept the first step that is in your life. You have a bit contributed to the analytic aspect in a paper about range manifolds. But how do you see this evolution? Do you think that it is completely normal? And how do you see yourself in this evolution?
Well, for one thing, I would say, I've written this recent long paper with Katrine Verheim about the fundamental foundations of Kuranishi structures. So I'm very involved, actually, in this sort of technicalities, even though my contribution was not analytic, but more topological. There seemed to be a lot of basic topological issues to be worked out, which I think are very interesting, and I think it's very important for the field to get these correct, because partly the field is so close to physics, and there are so many wonderful ideas coming from physics that without a grounding of, it's very easy to be careless. It's really hard to get things precise, and sometimes you really need new ways of looking at things, and people just haven't been careful enough. So I think it's actually very important to try and get the foundations issues correct, and there's definitely Hofer-Wysocki-Zane there is one way, and I think the old methods, which are still another possibility that one can make the old ways of doing this correct, but it still requires some work to polish the proofs, though perhaps the basic ideas are there, but the proofs are definitely not polished yet. And I think the field deserves to have correct proofs that are not just approximately right. Then the third aspect, all this algebraization and A-infinity categories and mirror symmetry, I would say is very exciting, but it's not clear it's for me. I don't have enough knowledge really to contribute in that area. I'm more interested, I think those ideas have something to say about specific geometric questions. And so, for example, I'm interested, you have this Lagrangian torus, can you displace it from itself? Is there a Hamiltonian isotopy that moves it off itself? That I find an interesting question, and I've made a few contributions there. But the other way of trying to find invariance to show that it can't be displaced, that has many repercussions, and I only understand a little bit of that. That's why I say symplectic topology is incredibly rich, because there are many different aspects. There's a dynamical aspect. There's just many different aspects of it. And it's too big for me to know all of it.